So I want to make sure I get a few more examples in, at least, yeah, 2 more examples in, of graphing rational functions where the degree of the top is bigger than the degree of the bottom. We haven't done any of these where we've graphed any of these yet. So these are a little different, I guess. Remember, when the degree of the top is bigger than the degree of the bottom, there's not a horizontal asymptote. Okay, so first, the first thing we want to do is factor the top. Do I have this written down correctly is the question. Yeah, I think so. So out of the top, notice there's a greatest common factor of x. There's an x in common. When we factor that out, we're left with, in parentheses, x plus 2. And the bottom, we just have a linear factor of x minus 3. Now I'm going to start with my vertical asymptotes. I'm going to take my bottom factors and set them equal to 0. I just have one linear factor here. It's going to give me a vertical asymptote at 3. This has multiplicity, odd multiplicity, has an odd multiplicity of 1. Because the largest power here is a power of 1 over x minus 3. All right, how about horizontal asymptotes? There are none. No horizontal asymptotes. Since the degree of the top is bigger than the degree of the bottom, the degree of the top, I'm calling f of x, is 2. That's bigger than the degree of the bottom, g of x, which is 1. Okay, so instead we're going to look at slant asymptotes, sometimes called oblique asymptotes. So you'll have a slant asymptote when the degree of the top is exactly 1 more than the degree of the bottom. That's what we have here, right? 1 more than the degree of the bottom. Get this to right, I'd be... Okay, there it goes. Okay, so how can I get this to work? Okay, that should give me enough space there, I think. So I'm going to take the top before it's factored, this part in blue, x squared plus 2x. I'm going to put a plus 0, a constant on the end. I'm going to divide that by x minus 3. And call this x out front yellow. I'm going to ask what times that yellow x will give me x squared. Well, obviously x. So I'm going to put an x up top in the x column. I'm going to take that yellow x I just got, and I'm going to multiply it by the yellow x out front. X times x is x squared. X times minus 3 is minus 3x, and we're going to subtract all of those. So I have x squared minus x squared is 0, and then 2x minus a negative 3x is the same thing as 2x plus 3x. So it's going to be 5x. Plus 0, bring down the 0. I'm going to ask the question, what times that yellow x out front will give me 5x? Well, 5. So I'm going to write a plus 5 up top in the constant column. So I'm going to do 5 times x. I'm going to get 5x. I'm going to do 5 times negative 3. That's going to give me negative 15. And I'm going to subtract these. 5x minus 5x cancels. Then 0 minus negative 15 is the same thing as 0 plus 15. That's going to give me 15. Now that 15 there is actually going to be my remainder because, why is that my remainder? If I get this to right, I'd be in good shape. That's my remainder right there. Why is that my remainder? Well, look at the degree of 15. The degree of 15 has a degree of 0. It's smaller than the degree of what you're dividing by x minus 3. So, in conclusion, you can say you can rewrite r of x as you take your quotient, x plus 5, plus your divisor, I'm sorry, not your divisor, your remainder over your divisor, 15 over your divisor. So this is another way to write your function. Rather than factoring it, you could write it in this strange way. And this yellow part here, that's called the slant asymptote. I'm going to circle that in green. So the slant asymptote, we're going to call it y equals x plus 5. So that's basically an equation of a line. So there's this ascending, this diagonal line that's an asymptote for your graph. Okay, let's find what are called x-intercepts. To find x-intercepts, we're going to go back to our factored form. You have two linear factors, right? You have x and x plus 2. We're going to set those equal 0. So x equals 0. It has an odd multiplicity of 1. And x plus 2, we set that equal to 0. Solve for x. You get x equals negative 2 is an x-intercept that has an odd multiplicity of 1 as well. Okay, so now we're going to find y-intercepts, or the y-intercept, there's just one. I'll use the factored version. I'm going to take y equals, I'm going to plug in 0 for x, blank times blank plus 2 over blank minus 3. Oops, plugging in 0 for x. So it should be a 0, and a 0 for all the x's. So on top, we're going to get 0 times 2 over negative 3. That's just going to give us 0 over negative 3. 0 divided by anything else is 0. So y equals 0 is an x-intercept. Okay, I think that's everything we really need so far to begin our graphing. The basic ingredients. So I'm going to put down my vertical asymptote at 3. I should probably extend this a little bit in the rightwards direction. That would be good. I have a vertical asymptote here at 3 on the x-axis. I have two x-intercepts, one at 0 and one at negative 2. What did I say? 0 and negative 2. I'm getting distracted by something else right now. So I have one here and one here. Those are my x-intercepts. What else? I have a y-intercept at 0. Okay, that's there at the same place as the x-intercept is 0. And I have a slant asymptote. Oh, slant asymptote. Y equals x plus 5. So y equals x plus 5 is going to be a line, right? It's going to have a y-intercept of 5 and a slope of 1. So we're going to start off with our y-intercept of 5. Well, 1, 2, 3, 4. Yeah, so I haven't really given myself enough space, obviously. Let's redo all of this from scratch. That can be a problem if you don't give yourself enough space. And that probably will be enough space, I hope so. So let's start over. Vertical asymptote at 3. X-intercepts at 0 and negative 2. Y-intercept at 0, which is the same thing as the x-intercept at 0. Okay, slant asymptote at x plus 5. So we're going to start off with the y-intercept of 1, 2, 3, 4, 5 for our slant asymptote. It has a slope of 1, right? The slope out front is 1. So imagine I'll put a black dot for this asymptote. We're going to go up 1, over 1. Up 1, over 1. Up 1, over 1. You can go down 1, left 1, down 1, left 1, so on and so forth. So you're going to get this kind of asymptote here, this slant asymptote. Well, there it goes. Okay. That should be good, I think. I'm going to erase this here from before. And make my vertical asymptote go up a bit this way. Okay, so I have everything here now, don't I? Yeah. I have my vertical asymptote at 3. I have my 2. Come on, don't do that. Please don't do that. My 2 X-intercepts at 0 and -2. I have my Y-intercept at Y equals 0. I have my slant asymptote. Slant asymptote is Y equals X plus 5. It's that diagonal line. So what do we know? We know those 2 X-intercepts. Let's find out what's going on to the right of 3 here. So to the right of 3, I'm going to pick a test point of 4. Let's call that a test point. At X equals 4, what is Y doing? Well, I'm going to plug into my function. I'm going to use the factored version, a blank times a blank plus 2 over a blank minus 3. I'm plugging in 4 for my X here. 4 times 4 plus 2 times 4 minus 3. That's the factored version right here. So when I calculate that on top, let's see, I'm going to have 4 times 6 over 1. So Y would be 24. So at 4, Y is going to be 24. Okay, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That'd be like way up here. Okay, so I just don't have enough space on this. So we're not super concerned with super precise accuracy. But if you can imagine 4, 24, where that would be, you go to 4 on the X and 24 on the Y, that would be like way up here. So your graph is going to do something like this. Okay, let's just imagine. Let's just imagine that this graph just kind of jumps. Oh, crap. Oh, let's just imagine it jumps here. This is the y-axis. So let's just imagine this is 24 up here. So even though it's really not 24, you can imagine that's 24. So 4, 24 would be like here. Okay, I'm going to make that red. And what has to happen is your graph up in this upper right corner has to approach the vertical asymptote here, and it has to approach the slant asymptote here. Now, what's it doing on the other side of the vertical asymptote at 3? Well, check on your vertical asymptote at 3. At x equals 3, the vertical asymptote had an odd multiplicity, so it's going to have opposite orientation about that vertical asymptote at 3. So it was going up on the right side of 3, so on the left side of 3 it's going down here, and that has to connect to the x and y intercept there. And at 0, remember when you had an x-intercept of 0, that one had odd multiplicity, so you're going to go across, and that has to connect to -2, the x-intercept of -2. And remember what's happening at -2. -2, you had odd multiplicity, so you're going to have to cross at -2. And then you have to go down towards your what's that thing called? Slant asymptote. So your slant asymptote has to be approached. There you have it. There's a general picture of that. Okay, so let's do one more rational function where the top is a little bigger than the bottom by 1. So I don't remember which one this was. Okay, this was x squared plus 2x over x minus 3. Okay, I'm going to do another one. That was a number 6. Let's do a number 7. So here my function is x squared plus 9 over x plus 3. And the first thing I want to do is try to factor the top. Turns out you can't factor the top, right? You can't factor that. Not factorable. If you tried to factor that, you could see that it's not factorable by taking x squared plus 9 and setting it equal to 0, and then you could try to solve this. Right? X squared. You could subtract the 9 from both sides. You get x squared equals -9. And then you get rid of the square root on the left, and you do plus or minus the square root of -9. But you have a square root of a negative number. That's called an imaginary solution. So it's not a real solution. Don't know what happened there. Okay, we're back. So when you have a square root of a negative number that's not real, come on. So those solutions are not real, so we don't have a factorable situation. When you get solutions that aren't real, square root of negative numbers, you're not factorable. So you can't factor the top. Okay, so first of all, we want to find the vertical asymptotes. So we set the bottom equal to 0. We get x equals -3 as a vertical asymptote, and that has a multiplicity of 1. So it has odd multiplicity 1. Okay, y, no, not y-intercept, horizontal asymptote. It doesn't have 1, right? No horizontal asymptote. And that's because the degree of the top, which is 2, is bigger than the degree of the bottom, which is only 1. So instead we'll have a slant asymptote that we'll have to find. There's going to be a slant asymptote here because the degree of the top is exactly 1 more than the degree of the bottom. So to find the slant asymptote, I'm going to take x squared plus 0x plus 9, that's my top. I'm going to divide into that, x plus 3. I'll make that x out front yellow. I'll call that the yellow x. I got to figure out what times that yellow x will give me x squared. Well, x, and I'll write my x here up top. Here up top of the box, and the x column, I'm going to take x times x and get x squared. I'm going to take x times 3 and get positive 3x. I'm going to subtract the blues from the yellows, and I will get x squared minus x squared cancels out, and I'm going to get 0x minus the 3x gives me a minus 3x. And I'm going to bring down a positive 9. I'm going to ask the question now, what times that yellow x out front? It gives me a minus 3x, so a minus 3. So I'm going to take minus 3 times x and get minus 3x. I'm going to take minus 3 times 3. I'm going to get minus 9, and then I'm going to subtract those. And the minus 3x's cancel. We're going to get 9 minus a negative 9 is the same as 9 plus 9. It's going to give me an 18 remainder. That's my remainder. That's my remainder because it's a smaller the degree than the x plus 3 that we were dividing by. So if I wanted to write this out, r of x, that's my function. Here's another way to write it. You can write it as x minus 3, that's the quotient, plus the remainder, divided by the divisor, x plus 3. That's another way to write my function. This is called in divided out form. So this yellow x minus 3, that's going to be my slant asymptote, y equals x minus 3. Now it's green. Okay, so we got our slant asymptote. Okay, now we want to do x-intercepts. So the top doesn't factor, right? We said it doesn't factor. So what you would just do, you would try to solve x squared plus 9 equals 0. And we know when you set that equal to 0, you would subtract 9 from both sides, which we've already seen. And to solve that, to try to solve that, you do plus or minus the square root of negative 9, which is not real. So since we don't have any real solutions, we don't have any x-intercepts. So there are no x-intercepts to this graph. That's possible. That happens sometimes. You never cross the x-axis. You never hit the x-axis. All right, so y-intercept. To find a y-intercept, you're going to set your x is equal to 0 in your function. So I'm going to use blank squared plus 9 over blank plus 3 and plug in zeros for my x's. So here I'm going to have, let's see, 0 squared plus 9 is 9 over 3. So we're going to have y equals 3 as an x-intercept. And let's begin with graphing. I hope this one doesn't go too far off the page like the last one. That's not nice. All right. Okay, so we're going to put in everything that we have. We're going to put a vertical asymptote at -3. We're going to put a slant asymptote at y equals x plus 3. So y equals x minus 3, rather, x minus 3. So that minus 3 is going to be our y-intercept for our slant asymptote. And the slope, so we have a y-intercept of -3, a slope of 1, so we're going to go up 1 over 1. So up 1 over 1, up 1 over 1, up 1 over 1. So we'll be here at 3. And we'll just connect those to draw out our slant asymptote. Okay, so that's just graphing the slant asymptote. Okay, now let's actually put in any points we have. We don't have an x-intercept, right? No x-intercepts. We do have a y-intercept at +3. 1, 2, 3. So I'll make that a red dot right there. So basically, that tells you everything you need to graph. So you have this point here. So rather than your rational function being down here in the left side, the bottom right side, it's going to be up here in the upper right side. It's going to do something like this. So it has to pass through the y-intercept, and it has to follow the asymptotes. The vertical asymptote here and the slant asymptote here. It has to follow those. So you're not going to have anything down here. Nothing down there. Otherwise, it wouldn't be a function, right? It wouldn't pass the vertical line test. So, what happens on the other side of -3? You have two possibilities, right? You could have something like this. That's one possibility. Or you could have something down in here, in the bottom left corner. Well, let's see what's going on about the vertical asymptote -3. The vertical asymptote at -3 has an odd multiplicity. So that means the orientation is opposite. So on the right side of -3, we're going up. On the left side of -3, we have to be going down like that. We have to be approaching it. So it's going to do something like this. Something to that effect. All right, so there's your function, R. You can't see this all on the same page.